Welcome, this is Professor Ridge, and today's lesson 6.1 Exponential Functions. And our first learning objective, evaluate exponential functions. Okay, identifying exponential functions. Alright, let's look at these two functions. If I have f of x equals x squared, that's a quadratic function, and f of x equals, now we're going to switch it, so we're going to have 2 to the x. So here, a quadratic function that we've been studying throughout this book is from our toolkit function. You know, if we have x, y, or f of x, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and we know about the symmetry. So if we did negative 1 squared, would be 1. Negative 2 squared would be the same as 2 squared, which is 4. Negative 3 squared is 9. And we should know pretty well that that graph looks something like, or just do a crude drawing real quick. I should do a little better one. But anyway, hopefully you're pretty well versed with the square function. Parabola. Okay. And then, now this is an exponential function. And notice the difference. Here the base is the variable x, and then you're squaring it. So even though they have the same kind of feel where you have a number to a power, the thing is, where's the variable? Here the variable is the base. Here the variable is the exponent. That's what makes it an exponential function. Now let's do the same numbers for this one and see how that one behaves a little differently. So 2 to the 0, anything to the 0 is 1. 2 to the 1 is 2. 2 squared, 2 times 2 is 4. 2 cubed, 2 times 2 times 2 is 8. So we're going to keep doubling this. It'll be 16, and then 32, so on. Now on the negative side, 2 to the negative 1, you got to remember your negative exponent rule. Anything to a negative exponent is 1 over a to the n. So this is going to be 1 over 2 to the first, which is 1 over 2. And then negative 2, 2 to the negative 2 power is 1 over 2 squared, which is 1 over 4. 2 to the negative 3 is 1 over 2 cubed, which is 1 over 8. And so the way this one's going to look here, I'll draw this one a little bit nicer. Let me pause. Okay, so let's plot these points here. So we're going to do 0, 1, 1, 2, 2, 4, 3, 8, negative 1, 1 half, negative 2, 1 fourth, negative 3, 1 eighth. And what's going to happen this way, if we did 4, it'd be 1 16th. We're cutting that distance in half. Then 1 over 32, then 1 over 64. It's just going to get closer and closer and closer to 0 as we move that way. So again, that's called an asymptote. We've studied that already. And then this curve is what we call an exponential growth curve. And you can see, if I were to layer this on top of there, you can see that this one grows a lot quicker. And then we can identify the domain for this one, for the exponential graph, is going to be all real numbers. But the range is just going, well, be similar to that one. It's just going to be the positive numbers. Oh, it's not going to be 0 though. This is going to get closer and closer to 0, but it's never going to touch 0. And I'll show you on Desmos in a minute. 0 to infinity. So it's greater than 0. We have an asymptote, so remember with our notation, the left side is approaching 0. As x approaches negative infinity, f of x approaches 0. Okay, so we have a horizontal asymptote. X, or y, sorry, y equals 0. That's our horizontal asymptote. Okay, so it's approaching 0 as you get, as x goes to negative infinity. Okay, so f of x equals 2 to the x. That's a basic exponential function. So this number 2, this base, could be any constant number. So we can kind of generalize an exponential function. It says here, for any real number x, an exponential function is the form of f of x equals a times b to the x. So let me write, kind of just to emphasize this, a times b to the x. This is the x. This is what makes it the exponential part, because the variable is up in the exponent for some real number b. Okay, now there's some conditions here. A has to be a non-zero real number called the initial value, and b is any positive real number such that b is not equal to 1. So if you think about that restriction, if b is 1, 1 to any power is just 1. So then this exponential part collapses and you just get y equals a, which is a horizontal line. Okay? So b can't be 1 for it to be an exponential function. The domain of f is all real numbers, so we talked about that. The range is all positive real numbers if a is greater than 0. Okay? The range of f is all negative numbers if a is negative. So if a is negative, it flips from, we learned from our transformations, it would flip the graph upside down. And then the range of f is all negative numbers. Oh, I just read that. And then the y-intercept is 0a, and the horizontal asymptote is y equals 0. Okay, so if you put in 0 for x, b to the 0 is 1, and then the y-coordinate would be a. So on the y-axis, it crosses at a. So the one we did here, the a was basically 1, and so it was 1 times 2 to the x. So when you put in 0, 0 squared, 2 to the 0 is 2 times, oh, I'm sorry, 2 to the 0 is 1 times the 1 in front would be 1. So it crosses at 1. Okay, so this number. Okay, let's look at example 1. Which of the following equations are not exponential functions? So which of them don't have basically what I look for is you want a variable in an exponent, right? As an exponent. So here you have the base of 4, and we're raising it to the power, or the exponent, 3 times x minus 2. So this is the x right here, the variable. So you can have just x or a variable expression involving some variable. Usually it's x, but it can be any variable. So yeah, that one's an exponential. Okay, x to the third. Now look at the variables of the base. Even though this is what is it? It's an expression with exponents. It's not an exponential function because the x is the base. We want the x to be the exponent, to be exponential. So this one's not exponential. And then here, 1/3 is the base, x is the exponent, so that one's exponential. And then here, -2 is the base, and x is the exponent, so that one's exponential. So only g of x is not exponential. The rest of them are exponential. Oh, J got me off guard because look it up here. I forgot one thing. A is a non-real zero number. It's called the initial value. B is any positive real number. So you can't have a negative base. The base has to be a positive number that's bigger, that's not equal to 1, right? So it can be 1/3, that's fine, but it can't be -2 or -1 or -1/2. Okay, so this one is not exponential. So that one got me because I wasn't paying attention. So that's a nice learning opportunity. Okay, example 2, evaluate exponential functions. Let f of x equal 5 times 3 to the x plus 1. Evaluate f of 2. So f of 2, we're going to take the x out and put a 2 there. And it says without a calculator. So we're going to do the x, simplify the exponent first. So think about that. You can think of it as a grouping symbol being in the exponent. So that's why I put the parentheses to emphasize. I want to do that first. 5 times 3 to the third. Now, order operations, remember you're going to do inside grouping symbols, so parentheses. Then you're going to do exponents. So you're not going to do 5 times 3. You do multiplication after you do exponents. So you got to do the exponents first. It's 3 times 3 times 3, which is 27. And then multiply it by 5, which would be 135. Okay, defining exponential growth. A function that models exponential growth grows by a rate proportional to the amount present. For any real number x and any positive real number a and b, such that b is not equal to 1, an exponential growth function has the form f of x equals a times b to the x, where a is the initial or starting value of the function, and b is the growth factor or the growth multiplier per unit x. Okay, so example 3, evaluating a real-world exponential model. At the beginning of this section, we learned the population in India was about 1.25 billion in the year 2013, with an annual growth rate of 1.2%. This situation is represented by the growth function p of t is equal to 1.25, see that's that initial amount, 1.012 t, which is the growth rate, where t is the number of years since 2013. Okay, to the nearest 1,000, what will the population India be in 2031? Okay, so 2031, so you got to figure out how many years. So t equals 0 is the year, here, let's do it this way. So here's the year 2013. So t equals 0. Now if I do 2014, that would be t equals 1. So if I want to do 2031, so 31 minus 13, that would be t equals, I think, 18. Let me double check that. Yep. Okay, so it's t equals 18. So now we're going to plug in 18 into this exponential growth model. So p of t for population is equal to 1.25 times 1.012 to the t. So basically, if you write this as a decimal, move it 2 places to the right, and then you're going to do 1 plus the rate, which is 1.2%. So you get 1.012. That's where this number came from. Okay, to the nearest, let's see, t would be 18 years. So then we just get out our calculator. Okay, again, Desmos has just the calculator portion if you just want to use that without doing the graphing part. Times, now you can put the parentheses or not the parentheses for this one. You can use them or not use them, it's up to you. And then power, 18. And as simple as that. Okay, so this is 1.54, they said nearest thousandth. So 1.549. And then you got to remember that that's in billions. So this would be 1.549 billion people in 2031. Okay, on to the next learning objective. Find the equation of an exponential function. Okay, so here's the technique. Given two data points, write an exponential model. If one of the data points has form 0a, then a is the initial value. Using a, substitute the second point into the equation f of x equals a b to the x and solve for b. If neither data points have the form 0a, we substitute both points into the equation, into two equations with the form f of x equals a b to the x and solve the resulting system of two equations in two unknowns to find a and b. So hopefully you remember how to do that. We're going to cover that again in a later section in the chapter, in the book. But hopefully you remember how to do that. Using an a and a b found in the steps above, write the exponential function in the form f of x equals a times b to the x. Okay, so let's try it with example 4. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an exponential function n of t representing the population n of deer over time t. So our initial value here, we're going to say t is equal to 0 when in the year 2006. So we're going to use that as our initial time. Okay, so they basically gave us an initial value. We have 80 deer at time 0. So this is t and this is n, the number of deer. And then they gave us a second data point, 2012, so that's 6 years later. Oops, 2012. So that's 6 years later. So that would be 6, and there was 180 deer. So now we're going to use this to write our function n of t equals a times b to the t. Okay, so now we're going to plug in the 80 for the a, and then plug in the second point, b, which is the 180, and for t is 6, and we're going to solve it for b. Oh, actually, I think I messed up. We're going to plug in the 80 for a, right? Because if you plug in 0 for t, so think of it this way. N of t is a times b to the 0, and that's equal to 80 right here. So b to the 0 is just 1, so that tells me a is 80. Okay, so now we can plug in, so I said it wrong a minute ago, but this is what you do. So you're going to plug in the 80 for a. Now you got to figure out what b is. So you're going to plug in the second point, remember, this is your n of t, n or n of t, same thing. So 180 is equal to 80 times b. We don't know. We got to figure that out. And b is 6. And we got to solve it for that. So the way you do it is you're going to divide 80. Okay, so let's see, the 80s cancel. So I get b to the 6th power equals, and then let's see, divide by 2, we get 9/4. Now, we want to isolate b using properties of exponents. So we're going to do, so if we raise both sides to the 1/6 power, 6 times 1/6 is b to the 1st, and then you just punch this in your calculator. And let me get my Desmos calculator out. So we want, what was it? 9/4. And then we're going to raise it to the 1/6 power. Let's see here. I don't know if this will work. Yeah, it does. So 1.14, if we go out 2 decimal places. 14, we'll go out a couple more. So b is about, put there squiggly lines, 1.1447. Okay, so now we can write our function. So the last step, we put in the a, and then the b is 1.1447, and then to the t. And that's our equation for the population of deer. Okay, now let's try the little harder example, 5 here. Write an exponential model when the initial value is not known. Find an exponential function passed through the 2 points, -2, 6, and 2, 1. So we have to use this idea here. If neither of the data points have its initial value, you're going to substitute both points into 2 equations with that form, and then solve the resulting 2 equations in 2 unknowns to find a and b. Okay, so that's a little more tricky. So if we have f of t, are we going to use t or are we going to use x? We're going to use x. All right. So f of x equals ab to the x. We're going to plug both these points in. Remember, this is x, f of x. X, f of x. And remember, f of x is just y. Same thing. So we're going to put the 6, ab to the -2. So that's our equation 1. And now using point 2, we're going to put in 1 for the f of x, ab to the 2. Now we're going to solve this system. Okay, so you should know, usually through intermediate algebra class, you should know how to solve a system using substitution, elimination, graphing. Hopefully you learned some of the matrices stuff with Cramer's rule and using a matrix equation. But anyway, so let's just do the substitution one, probably be the easiest. So we're going to take equation 1 and we're going to solve it for a or b, it doesn't matter which. A is probably easier. Let's see what the book did. Yeah, they solved it for a. So you're going to divide both sides by solve for a. So you're going to divide both sides by b over -2. So those cancel. And then this, you can simplify. You should know b to the negative 2, I can move it to the top and change the sign of the exponent. So b squared. So now you're going to take this expression and substitute it into equation 2, which is 1 equals ab squared. And I'm going to take this expression, a, and substitute that. So 1 equals 6b squared times b squared, which equals b to the 4th using exponent rules. Add the exponents if the bases are the same. I hate when there's 6's and b's because my b's and 6's tend to look alike. So you just got to make sure you know the difference. We're going to solve for b, so divide by 6. And then you're going to raise both sides to the 1/4 power. So b, 4 times 1/4 is b to the 1, so that's b. And then we get out our calculator, 1/6 to the 1/4. One 6 to the 1/4 is 0.6389. 0.6389. Okay, and then we're going to take this and plug it back into that equation to find out a. So a equals 6 times 0.6389 squared. Now, if you leave things in your calculator for a minute, instead of me to get a more accurate number, you want all those numbers. Now I'm just going to square this whole thing. So I'm going to put parentheses around this and square it. And I get 0.4082. And then times 6. Right? Square it and then times 6. So I get 2.4495. Right? Now the book, they use the rounded number. Here, let me show you the difference. So the book used the rounded number here. So it depends on how accurate you want things. So let's see. Oops. It was 0.6389. And then we square that. And then times 6. Times 6. And you can see how it's 24491, which that would round to 2. So this is the answer they have in the book, but this one's a little more accurate. So 2.4495. So I'm going to use the little more accurate one. So that's going to be about 2.4495. Okay? So now I can write my function. I have my a and b, so I'll plug it in here. So f of x is a, which is it's 2.4495 times b, which is 0.6389 to the x. And that'll be my answer here. All right, let me show you the graph of this function on Desmos, and that it does go through those 2 points that they gave us. So negative 2, 6, and 2, 1. So here's the graph. F of x is 2.4495 times, see, you don't need the parentheses because the exponent you do first, and then you times it. Okay, so here's the function we found doing the algebra, and you can see it crosses, so the red line, that's exponential. This is, by the way, This is called exponential decay. We'll talk about that in a little bit because it's decreasing through time. And it goes through those 2 points. Okay. So the technique, given a graph of an exponential function, write its equation. So basically it's the same idea. You have to identify 2 points on the graph. Choose the y-intercept as one of the 2 points whenever possible. Try to choose 2 parts that are as far apart as possible to reduce your round-off error. And basically you're going to do the same technique with the algebra once you identify those 2 points. Okay. All right, so let's try one. Okay, so example 6. Let's see if we can identify the y-intercept, which is 0, 3. 0, 3. And then we want one other point far away if we can. That looks like a nice point, actually. 2, 12. 2, 12. And then we can say, all right, so now we're going to do, since we identified the y-intercept, we can do, it's the easier technique, right? So you're going to let A, basically, again, we have f of x is equal to a, b, x. And remember our points, we have x, f of x, x, y. So if it's 0, 3, so if you put in 3, you can think it's the same technique. It's just when you put in 0, 3, it automatically gives you A, because if you put in 3 for y, b to the 0 is just 1, 1 times A. Times A. So A is 3. So now you know f of x is equal to 3bx. Now to find b, use the second point, 212. So once you understand that, you can skip this work and just go straight to here. That's what the technique says in the writing on the previous page. So we're going to put 12 in for f of x. B we don't know, and x is 2. So divide by 3. So b squared equals 4. And then we're going to raise both sides to the 1/2 power, or another, that's the same thing as saying you're going to square root both sides, right? But we're not going to do plus minus, we're just going to do the positive. We just want the positive one. So if we do 1/2 power, 1/2 power, or square root, same thing, you get 2. So b is 2, because remember the base has to be positive, so that's why you don't do the plus minus. So our equation would be f of x equals 3 times 2 to the x. Okay, so the book gives it shows you how to do it with technology using a TI calculator, TI 82, 83, 84, so on, right? Depending on which ones you have, all the way up to 92. Basically, this is the technique. I'm not going to go over that because I didn't require you to have one of these, but I'm going to show you how to do it on Desmos. So if you're given just 2 points, so again, it's called regression when you want to do the best fit line. So if they gave you just 2 points, you could do, and they told you it's exponential, the way you would do it on Desmos, let me get the Desmos here, you're going to put in the 2 points, but you're going to put it in as a table. Okay, so you hit add, table, and basically the L1 and L2 in your TI calculators, L1 would be your x coordinates, L2 would be your y coordinates. So this x sub 1 is basically L1. Okay, so now what we're going to do is put in the 2 points. We had 2, 24. So 2, let's see. Let me move. Okay, so let me put in the x is 2, y is 24.8. Enter, and then my next point will be 5, and then 198.4. And now what you're going to do here is you're going to say y, and then you're going to use the tilde button. So let's see, tilde. And then you're going to put in the form a b to the power, where's my keyboard thing? Here we go. To the power x. Oh, and I should put y1, so you just type in y1, and then this should be x1. Oh, and then the other thing you can do with your table, let me go back to this table. Oh yeah, it's there. Okay, and then you get, let's see here, it tells you what A and B are. So A is 6.2 and B is 2. What I was trying to do is, what were the 2 points? 224. See, there's that one. And then the other one is 598. 198, sorry. Way up here. Okay, so you can see that graph definitely goes through those 2 points. Let's zoom out regular. Thank you if you hit home. All right, so that's the exponential model that will fit those 2 points. So A is 6.2 and B is 2. So nice quick way to do it with technology. So again, our final answer would be y is equal to 6.2, or you can say f of x, times b was 2 to the x. Okay, so that's our exponential equation. Okay, the next objective, use compound interest formulas. Okay, the compound interest formula, compound interest can be calculated using this formula. A of t equals p, parentheses 1 plus r over n, parentheses, raised to the nt power. So when you type this in the calculator, you should probably put parentheses around the exponents. Okay, A of t is the account value. T is the time in years. P is the starting amount in the account, called the principal, or more generally present value. So finance, we'd call that present value. R is the annual percentage rate, or APR, expressed as a decimal. So you change it from percent to decimal. Remember, you move it 2 places. So from percent to decimal, move it 2 places. So if I had like 5%, you put the decimal point there. You're going to move it 2 places that way. So it'll be 0.05 as a decimal. And then N is the number of compounding year periods in 1 year. So if N is, compounding periods is monthly, then there's 12 months in the year. N would be 12. Daily would be 365. Monthly, 12. Weekly, there's 52 weeks in a year. If it did it quarterly, 4 quarters a year. Okay, so depending on the periods per year in 1 year. Okay, example 8, calculate compound interest if we invest $3,000 in an investment account paying 3% interest compounded quarterly. So N would be 4. How much would be in the account in 10 years? So let's see, we have 3%. So that's 0.03. I usually don't write that first 0. I've been doing it more lately, but 0.03. But again, it's not necessary. So I'm going to do this formula. A of t is equal to principal, so 3,000 that I invested, 1 plus R is the 0.03 over N, which is quarterly, so 4, and then 4 times T. So that is our general formula for this specific account. Invested 3,003%, and now we want to know how much will it be in 10 years. So you plug in 10, and then 1 plus, you can make this one decimal number, right? Just type it in, and then you'll get 1 point whatever. I'm just going to leave it this way and just type it in decimals exactly like this, 4 times 10. Okay, so let's get decimals. Not the graphing one, the scientific one. And we will put in our formula here. So let's see, what was it? It was 3,000 times parenthesis 1 plus 0.03 divided by 4, close parenthesis. Oops, you got to make sure you're in the right spot here. So let me get rid of this. So 4, and then the power, parenthesis. I think with decimals you don't need those parentheses, but a lot of calculators you will. So I just put them in just in case. So it's 4 times 10, and then close parenthesis. And you get $4,045.05 if you round it to the nearest cent. So A of 10 is $4,045.05. So with money, you typically round it to the nearest cent. So there you go. So that's our final answer there. Okay, using compound interest formula to solve for the principal, a 529 plan is a college savings plan that allows relatives to invest money to pay for a child's future college tuition. The account grows tax-free. Lily wants to set up a 529 account for her new granddaughter and wants the account to grow to $40,000 over 18 years. She believes the account will earn 6% compounded semi-annually, so that's twice a year. To the nearest dollar, how much will Lily need to invest in the account now? So she's going to put a lump sum in an account and let it just sit there and grow over 18 years, and then she'll gift it to her granddaughter to go to college. So let's see here. So we have this formula equals principal 1 plus R over N to the NT. So let's plug in what we know. We don't know principal. We want to solve for that. 1 plus, she believes she's going to get 6%. N is twice a year, so that'll be 2T. I'm not going to write parentheses this time. And then we want that to be equal to 40,000. 40,000 in how many years? 18 years. Okay. So we're going to solve for P. So we punch this part in our calculator. So 1.06 divided by 2 to the 36th power, or 2 times 18. I guess I should be showing you what I'm doing here. So I just putting in 1 plus 0.06 over 2 to the 2 times 18. So it's 2.898. We'll just go out 3 places. 2.89, 2.898. 2.898. That's this whole expression times p, and you can move the p to the back, no big deal. And then you just divide 2.898, 2.898. So p is, so I'm going to do 40,000. Oops. Okay, so here's a little thing about decimals too. So I want to do 40,000 divided by 2.898. And again, remember I said if you leave things in your calculator and you want it a little more accurate, you just type in A and S for answer, and it'll take the last answer. So 40,000 divided by 2.898278328 is 13,000. So she needs to deposit about 13,800 in an account, and it will grow to close to 40,000, right? And we're just these are just estimates anyway, so I'm going to round it to the nearest. Oh, they want nearest dollar, so 13,801. All right, so she'll need to invest $13,801 in 18 years, assuming that she gets the 6%. Will be 40,000 in 18 years. And using our last learning objective, evaluate exponential functions with base e. Okay, the number e, the letter e represents the irrational number 1 plus 1 over n to the n as n increases without bound. So if you put in 1 for n, and then 2, and then 3, and then 4, so on, and watch as it increases, as n gets larger and larger and larger, this number is going to, we call it the limit's going to be this number 2.7182828. Okay, it's named after Swiss mathematician Leonhard Euler, who first investigated and discovered many of its properties. So he was in the 1700s. Okay, I just want to show you how that works. So 1 plus 1 over x to the x. So I just changed n to x. I can use decimals. So you can see, so if I put in 2, f of 2 is 2.25. So 1 plus 1/2 squared would be 2.25. And then if I put in 3, 4, you can see how that's growing. Okay, and then let's put in, okay, let's jump to 10. And you can see that's 2.5, now 100, 2.7, 1,000. So as we get larger and larger and larger, 1,000,000, or whatever that is. Yeah, that's 1,000,000, right? And then, you know, keep putting in zeros. And you can see it's kind of flattening out. It's not growing very much, and it's getting to that limiting number e, which is the 2.71828. So we're almost, I mean, we have that, but if you were to do e, if you just type it in e, 2.71828182846, and it goes on forever and ever and ever. If I were to graph the line y equals e, see this purple line, the values from this table will never cross that line. It's going to be limited. That's why we call it limit, by that value 2.71828182846, going on forever, e, which is, so basically you let x grow as large as you want without bound. As x goes to infinity, right, the value is going to approach this number e. Okay, so that's an irrational number, and that's what that's saying there. Okay, use a calculator to find powers of e. Calculate e to the 3.14. Now, every calculator a little different, right? There's a few different forms. So some of them you'll see this button. So it depends. You have to look at your calculator. You may have LN, And then above it will be written e to the x or e to the n or just e with a power symbol. Like it might say something like that. Some calculators will have this button, and you hit that button. So you have to look. So if it's written above it, you have to, typically you'll have a button that says second or let's see what else, alternate, or it just depends on the calculator. They all have different things. So what you do is you would hit second this button and then whatever the power is, or you would hit this button without the second because it's an actual E button, and then you hit the button and then you put 3.14. Some calculators you got to do it backwards. You put the 3.14, then you hit second ln, or if it has this button, you just hit that button. So you got to experiment with your calculator to make sure you know how to do it, or just Google it. Desmos is super easy because, again, you just type in E, and that's E, and then the power, and then you type in 3.14. Okay, you won't be able to use Desmos on your final, so make sure you learn your calculator how to use the E button, the LN button, so on. So they wanted 5 places, so 23.10386, and then round it, so that 6 would make it 7. Alright, so this would be E to the 3.14 will be 23.1038. Okay, that's 1, 2, 3, 4. So this is the place I want to round to. So I got to look at this, the next place. It was 6, 6. So this will round up to 7. So 23.10387. The continuous growth and decay formula for all real numbers t and all positive numbers a and r, continuous growth or decay is represented by the formula a of t is equal to a times e to the power rt, where a is the initial value, r is the continuous growth rate per unit time, and t is the elapsed time. So if r is greater than 0, the formula represents continuous growth. So that's exponential growth, or in this case we call it continuous growth. If r is less than 0, if it's negative, then the formula represents decay, continuous decay. For business applications, continuous growth formula is called the continuous compounding formula and takes the form a of t equals p e to the rt. So you hear people say PERT because that's what it looks like, PERT. Okay, so p, principal, your initial amount, initial value, which is the same as a for amount, and then e to the rt, where p is principal or the initial invested, r is the growth or interest rate per unit time, and t is the period or term of the investment. Okay, so given initial value, rate of growth or decay, and time t, solve a continuous growth or decay function. So here's the technique. Use the information to determine a. Use the information problem to determine the growth rate. If the problem refers to continuous growth, then r is positive. R is greater than 0. If it's decay, your rate's going to be a negative number. Okay, so make sure you understand that. Use the information problem to determine the time t, and then plug everything in. Substitute the given information into the continuous growth formula and solve it for a of t. So let's look at this example 11. A person invested $1,000 in the account, earning a nominal 10% per year compounded continuously. How much was in the account at the end of 1 year? So a of t, we're going to do the PERT one because it's money. I mean, it doesn't really matter. You can still call that a, same thing. So initial amount is the a or the p, principal. R is your growth rate per year. So 10%, 0.1 or 0.10, same thing. You should understand that. A lot of people get confused, right? You can add as many zeros you want at the end of a decimal number. That's all the same thing. T. Okay, now how much does it count at the end of year 1? So we're going to plug in 1 for T. So it'll be 10,000 e to the 0.10 times 1, which is just 0.10. And we're going to punch that into our Desmos calculator. Let's see here. Enter. So it was 1,000 times e to the power 0.10. Now, make sure with your calc you probably need the parentheses. I don't think we need it here for this. For Desmos, I think you can handle it. Times 1. Notice how that didn't change whether I typed the 0 or not. It's going to give me the same answer. Times 1, which is, again, it's not going to change the answer. So I didn't even need to type that. So we get 1105.17. So 1,105, $1,105.17. Okay, so example 12, calculating continuous decay. So decay, remember the rate's going to be a negative number, so you got to take the 17.3 and make it negative. How much radon? How much will 100 milligrams of radon 222 decay in 3 days? So this is the rate per day. So the time is in days. So we have A of t equals, now we're going to change the P to A. You can leave it at P, it doesn't matter. E to the RT. So we're going to plug in the initial amount is 100. E to the R is negative 0.173. Remember, you got to move decimal place 2 places, times T. So this is our equation, or exponential decay, and we want to know at the end of 3 days. So we'll put in 3. And again, you probably need to use parentheses depending on your calculator. So I like to write that. So we had 100 milligrams e to the point. Oh, it was don't forget the negative. Negative 0.17, what was it? 173 times 3 days. That's the other nice thing with Desmos. You can just, again, if you leave stuff in your calculator, then you can kind of use it. So 100 times e to the negative 0.173 times 3, so it'll be 59.51. How many places do they want? They didn't say. So rule of thumb, if they don't say, I usually go to 3. That's pretty safe. Or I do the same number of places for whatever my problem used, right? So again, 3 is probably pretty safe. So 59.512. And I said 3, and the book did 4. So the book, if you look at the answer in the book, 5115. Same, you know. So 3 or 4 places. Typically I do 3, but again, it's up to you. Okay, that brings us to the end of the lesson. So again, make sure you practice, practice, practice. Go to the end of the exercise set in the book and do all the odds and then any other ones you feel you would like to do. All right. Have a great day and see you next time.